when we had a triangle starting from this side, we could always know that the starting point was 0 and the maximum point was on the other side. But this is not the case. If we take a segment here, this is not a triangle anymore. You can see it. It's not a triangle anymore. So if it's not a triangle, we probably cannot use the equation for a triangle. But the good thing is that I can still convert it into a triangle and a rectangle. So I would have this load would be sum of two loads now. Virtually, it's not actually the case, but we just know that this is possible. One is the triangular load and the other one is our rectangular load. So that is the only different thing about this problem. And once we say that this is one of the load is the triangular load and one is the rectangular load, we know that they will have a different point of action, because for the rectangular load, the center point will be somewhere here. So I would have a force acting vertically downward because of this rectangular load or UDL. For the triangular load, the centroid is somewhere here, 1/3 of the distance from this side. So this would be the second force, that would be F2. So that means when I take a segment, although my original loading is a triangular loading, but once I take a segment, the left side of the segment doesn't stay as a triangle. So if it doesn't stay as a triangle, that means I need to do some additional things. So what I did, I converted into one rectangular load that became a UDL and one of the triangular load that would be completely different. So this will be computed as 1/2 base times height. This is just a triangle, so we can compute it. So this triangle would have two components. There's a side of this that would be, let me call it the Y side, and this total side is W0. So I can see that the maximum load on the triangle side would be what? W0 minus Y, right? And this would be Y as well. So, and this length as usual, because whenever we take a segment, this length is X, so this length is X. So I need to find out these two additional forces. Let me compute the forces separately, and then we will solve the problem. So there's only one segment, so I don't need to write segment A, B, or B, C. There's only one segment there's only one load. So again, I will use the force F1. F1 is easier. That is just because a triangular load, so a rectangular load, so it is just base times height, X times Y. So I need to find out what is Y. So Y I can compute using these triangles, just like the last case we did. We said that we can use that the sides of similar, the ratio of the similar sides, ratio of the sides for the similar triangles would be exactly the same. So for the larger triangles, this ratio is W0 over Y over L. Everybody with me? So this is the height of this triangle, and this is the base of the triangle. Side is not showing. All right. So this ratio divided by this ratio must be exactly equal to this ratio divided by this ratio. So this side is how much? W0 minus Y, or let me write it. This ratio divided by, let me write this one, Y over L minus X. Is that right? Everybody gets that? Yeah, that's good.
Yes, sir. Yes, sir.
So Y is equal to W naught over L times L minus X. So that means my force F1 would be equal to X times Y would be equal to W naught over L minus X. Or systematically W naught over L and Lx minus X squared. This is force F1. Similarly, force F2, that is my triangular force. That is always equal to half time base. Base is X and height is W naught minus Y. So let's put in the numbers. 1 over 2x W naught minus Y would be equal to W naught over L minus X. 1 over 2x. This is W naught minus W naught. L will be cancelled plus W naught X over L. X over L. These will be cancelled. So it is 1 over 2x times W naught X over L. Simplifying, I can write W naught over 2L X squared. So I have these two forces. Let me write it here. F1 is equal to W naught over Lx minus X squared. And this W2 is equal to W naught over 2L X squared. So I have these two forces. Once the forces are computed, I can easily go back and write my shear force and bending moments relationships. So the shear force, again, I have to sum up all the forces. Sum of all the forces in the y direction on the left side. And we said there are two forces. So basically it's F1 plus F2. Both are acting vertically downward, so they would have negative signs. So it will be minus W naught over Lx minus X squared, and then minus W naught over 2L X squared. Let's try to simplify it if we are able to. This will become minus W naught X, that will be cancelled, plus W naught over L X squared minus 1 over 2 W naught over L X squared. This will become minus W naught X plus 1 over 2 W naught over L X squared. This is B. Because this is half and this is full, so we know this would be here. Are we good?
Yes, sir.
Good. Wonderful. Similarly, the bending moment. We just have to multiply these forces with the distance. So F1 times what? F1 times distance. What's the distance? Anybody who is
X by 2.
X by 2, yeah. This is F1 is just rectangular load.
1 by 2.
Yeah, 1 by 2. Or not 1 by 2, X by 2 actually, right? Half of the X, because this distance is X. So this distance is X, so this distance from this point